Good morning, everyone. Really happy to be here. Oh, sorry, I cannot move. Okay, I'll start over again. Good morning, and it's happy to be here again. And I want to share with you some of the lessons learned from managing OpenSearch at scale at SAP. For historic reasons, SAP, for the BTP observability service, hosted a single large Elasticsearch instance, our OpenSearch instance, and this prevented us from exposing the complete capabilities of the software to our customers. We had the common issues like the shards, and we had scaling issues, and we could not restrict them properly using authorizations so that we could give the full potential of the software to our end users. To overcome these limitations and also to scale the infrastructure, we decided to go with multi-instance setup from the multi-tenant setup. So this is the reason why we have one OpenSearch instance per customer. And in this talk, I would like to explain the details of how we manage the scale, and also pick some of the pain points that we faced and how we try to address them and so on. Before I start, I would like to know how many of you here use Kubernetes to host your OpenSearch clusters? Nice. And how many of you are already using open source OpenSearch operator? Right? Okay. All right. Let's jump into it. So yeah, here I want to start explaining about our OpenSearch setup, the scale and the environment we run in and deploy on, the challenges that we face, and some of the improvements that we did, and want to close with some of the outlook that we plan for as the next step. For those who did attend the keynote yesterday, the next few slides might be a repetition, but please bear with me. So the environment that we operate in is the SAP Business Technology Platform, the one that you see on the left. So BTP is SAP's platform as a service offering that comes with a comprehensive set of services, tools, and runtimes that allows customers across the globe to build intelligent enterprise applications and extend and integrate them as well. So there is quite a need for observability in this scenario to ensure the reliability of the systems and performance of the services are easily monitored and tracked. So in the middle, we see three different personas that need to be addressed. From the bottom, it's the platform operators, the one who maintain business technology platform, the service providers that host business services on top of this platform, and the yellow one on top is the customers that build their business applications on this runtime. So the observability need needs to cater to all three personas. On the bottom, you see the characteristics of such hosted observability service. It starts with it being a hosted service. So we need to alleviate the need for the application developers and service owners from learning the details of an observability service, hosting them, doing day-to-day operations, and so on. So it needed to be a hosted service. And the second step, it had to be out-of-the-box content. So on one end of the spectrum, there are users that need smooth integration with the different platform runtimes that is available. So we have to understand the ingestion and shipping needs of a different runtime, tie up to that needs, and then ingest data into OpenSearch. And when these users open their OpenSearch instance using OpenSearch dashboards, they would like to see pre-built contents. Like if we have Cloud Foundry-based runtime, then we offer Cloud Foundry runtime-based visualizations. For example, Cloud Foundry metrics, 4 golden signals, how good is the Cloud Foundry router responding, what is your response rate, and so on. And the other end of the spectrum, we also have users that need full OpenSearch capabilities. So they simply say, give me the complete capabilities of OpenSearch, and I would take care of performing complex queries, building my own dashboards, and using them. For these kind of users, then we simply provision the OpenSearch clusters, tune it for high ingest use case, and hand them over to it. So our service needs to cater to both these range of customers. The third one is the compliance need. In most cases where we run business applications or critical applications, it needs to be it needs to have proper encryption, proper authentication and authorization mechanisms. It needs to have strict retention policies. So if the customer mentions that it has to be retained for 10 days, we should delete the old ones after these 10 days. And also strict privacy separations. And last but not least, the standard or futuristic protocols that we need to support. So we see growing list of services and runtimes and capabilities within the platform. So it gets crucial that we evolve and adapt a unifying standard like OpenTelemetry, and which allows us to easily correlate and unify data, how the data is shipped and how the data is correlated across a variety of suites and runtimes. So OpenSearch, with its capability, with its observability capabilities, and also support for OpenTelemetry, is the best fit for powering our SAP Cloud Logging service. With OpenSearch in the background, SAP Cloud Logging service offers a comprehensive observability solution based on logs, metrics, and traces. It aims to serve the application developers, the service providers of the BTP runtime to monitor and perform analytics on their workload. After quite an intensive assessment internally and also looking at the adoption of our service for a few years, we launched the service public in December 2023. Like I mentioned, the unique selling point of our service is its ability to cater to non-observability users or business users that offers out-of-the-box experience for the runtimes that they are operating in. The advanced data processing and customization needs were also fulfilled thanks to OpenSearch's capabilities like anomaly detection, alerting, and ISM policies, retention policies, expressions, and all those things. We also expose all these advanced capabilities to our customers. That's the background, and let's start looking into the setup of our OpenSearch, of our service. So we have on the leftmost side the source systems which ship telemetry data. So in BTP, on top left, you see we have Cloud Foundry runtime, we have Schema runtime, where we have workloads running natively on Kubernetes, and there are other runtimes and legacy systems. So each of these runtime speak their own protocol. There is ongoing efforts and growing investment into OpenTelemetry to standardize all of these, but at the current time, there is a combination of both. Like, for example, in the first box, runtime specific, in Cloud Foundry, Logarithm ships in both HTTP or TCP in a CF syslog format. So it's a simple HTTP request with the payload being in a CF syslog format. So that's a specific one, and we need to build parsing and ingestion tailored to that. And for other users, for example, hosting workloads on Kubernetes, they use FluentBit or FluentD to ship their logs. And we have OpenTelemetry shippers as well active in the platform, and we have OpenTelemetry collectors shipping towards the cloud logging as well. We, from the cloud logging service, also offer instrumentation support for different sources. For example, we offer open source libraries to format proper to ensure proper log formatting. In some cases, we also support automatic detection of the availability of the service endpoint and configure them into your shipping libraries and so on. So we offer detailed instrumentation support through these libraries. And the middle layer is the ingestion layer. So this contains two components at the moment. So the first one is FluentD. We started the service by using FluentD. The FluentD supports different formats, like JSON. When somebody ships logs in a pure JSON format, it's able to read them and ship it to OpenSearch. We have custom support, like for CF syslog, where it parses the HTTP body to get the syslog formatted message. So custom parsing for Cloud Foundry. And many such additional custom parsing logics are part of the FluentD ingestion. We also added then, later in time, the data prepper supports. So with adding data prepper to our ingestion layer, we are now able to support OpenTelemetry ingestion. At the moment, it supports gRPC protocol, and we are working with community to also support HTTP there. So here with the FluentD and in the ingestion layer, we also take care of correlating or adding metadata that's SAP correlation, SAP-specific correlation, which comes in handy in the later stage when we do visualizations. And the rightmost layer is the backend, which is OpenSearch and OpenSearch dashboard, where the final train happens. And within this OpenSearch clusters, we offer then the pre-built contents that I spoke about. The pre-built contents include dashboards, visualizations. We also have getting started index templates, ISM policies for common use cases, and so on. We also offer several other additional service quality dashboards that that gives the customer out-of-the-box insights about how good is their cluster performing and so on. So all of this is bundled as a service, and this is the cloud logging service. And the users of the cloud logging service go to the marketplace and say, I want a cloud logging service instance from the marketplace of the runtime. And they simply select the size of the instance. For example, they say, I need a cluster that's 10 terabytes large. I need a cluster that's 100 gigabytes large, and so on. So we have different sizing, and customer gives his desired sizing. So we start always with a bare minimal size with 2 data nodes, and we scale out to full to meet the sizing needs of the customer. And the customer brings his own IDP, either a SAML provider or OADC provider, and during the instance creation, he just gives the details of his identity provider, and we take care of configuring it and connecting it for them. And once we do all the provisioning of the hardware, sizing requirements, IDP integration, and data OpenSearch is ready, we give back to the users the API endpoints, the OpenSearch dashboard endpoints, and we automatically take care of injecting the credentials into the runtimes of the applications. So they can also start shipping the logs. So this is the overall setup of SAP Cloud Logging Service. To talk about the scale, currently we run over 11,000 OpenSearch clusters, or 11,000 cloud logging instances across the globe. Each instance hosts its own OpenSearch database, OpenSearch cluster, and the surrounding process and other components. Since OpenSearch is a data-intensive workload, we need persistent volumes, and we have around 60,000 persistent volumes. This is really important because the number of volumes is crucial when you are running, for example, a version update of the underlying operating system and so on. It has an impact on how many volumes can be attached and detached within a short amount of time. With overall storage, we support close to 5 petabytes of storage. This could be large, but we also curate or delete the old indices based on the configuration that the customer chooses. So this workload is running on more than 20,000 instances, All of them are not EC2, but most are from EC2. But we use similar flavored machines on different hyperscalers as well. And we use, like I mentioned, Kubernetes to host our OpenSearch workload. So currently there are 46 to 50 Kubernetes clusters. So we use multiple Kubernetes clusters to host our workloads. And this setup is distributed across the globe on 20 different data centers and mainly concentrated in United States and Europe. So this is the current scale that we are managing. And there also comes the heterogeneity. So while we predominantly run on AWS, there are also other infrastructure providers that we rely on. So we run on GCP, we run on Microsoft Azure, and there are also SAP internal data centers that we also host our service on. And while most infrastructure providers provide 3 zones, there are cases where we have to adapt our deployments to also serve 2 availability zones. So we cannot have something as strict as, let's say for cluster manager, you cannot say it has to run on 3 different availability zones. Then this will never deploy on a hyperscaler with 2 availability zones or a special setup with 2 availability zones. So we also take into account the number of availability zones where our software is deployed. And interestingly, we also observe difference in disk performance. So when we choose same sized machines, there is difference in disk IOPS across different providers. So we also have to see and perform tests before we launch on a particular hyperscaler on what is the minimal required disk performance to have a smooth performing OpenSearch cluster. As you all know, OpenSearch is as fast as the slowest node. So this is also for us important. And the fourth thing that adds complexity is the sizing. So we have Kubernetes cluster, and it is easier if we have fixed size OpenSearch cluster. Let's say we are going to have a 100-node cluster, and it's going to be 2 terabytes each. Then it becomes easier. But what we have and what we offer to customers is different T-shirt sizes. So we have clusters that scale from 200 gigabytes to 1 terabyte, and there are clusters that scale from 2 terabytes to 10 terabytes. So let's say it's a small cluster, medium, and large, so different flavors that we have. So, and also the resource utilization of these different plan sizing are different. For example, the data node that hosts a 2 terabyte disk has more resources, CPU and memory, compared to the other one. So this makes the planning for resources on the machine level a little bit complicated. So we have to plan for optimal packaging and also scaling of them. I'll talk about that in the later slides. And then, like I mentioned, we have to support different protocols at the ingestion layer. Okay, going back to the slide, going back to the overall setup. So this is now a simplified high-level view of what we deploy when it comes to a cloud logging instance. There are other parts around it that supports these systems, but for simplicity reason, I keep them out. Let's start going one level deep into a single instance. First thing is we deploy the persistence layer. So we have obviously 3 cluster managers, or previously called masters, and we start with 2 data nodes. So this is the same for any size of OpenSearch cluster. And let's say the data nodes are 100 gigabytes each, so now we have 200 gigabytes. And the customer has configured, I want close to 1 terabyte of storage. Even if he has given this scale limit, we start with 2 gigabytes, and we keep adding data nodes as it gets filled up. So we use disk usage-based auto-scaling to scale out the OpenSearch data nodes. So some customers might say, I need 600 gigabytes. So we stop when there is 6 data nodes. So the disk-based autoscaling takes into consideration what is the configured limit that the customer needs, and then it stops at that point. We also have autoscale in, where when we detect that there is curation, or when there is enough room to scale in, then the autoscaler kicks in and deletes the latest data nodes. It does so by safely evacuating the node, and it waits for the evacuation to complete. And once it guarantees that there is no movement happening around with this target data node, it then removes the node from the cluster. So this gives flexibility to our customers to have an upper limit on how much they want to spend, and at the same time, they are not always spending the maximum, and it gets reduced if they are not using it to the fullest. The next is the OpenSearch dashboard deployment. So this is stateless, and we deploy as a Kubernetes deployment with one replica. So there are two OpenSearch data. And the ingestion, we start with, as well, we follow the same logic. We start with 2 Fluentd pods running, also stateless. And we also give the configuration option to customers to define an upper limit on how many Fluentd pods do they need. This gives the end user the flexibility to define an upper range on how many Fluentd would they need. And this will only scale out if there is a need to scale out, and for example, to handle a sudden burst, or if there is during certain period of the day, the ingestion is higher and they want to scale down, let's say in the evening or in the nights, then we will automatically take care of this from the users. So they can define an upper limit based on their cost restrictions. For Fluentd autoscaling, we use the built-in horizontal pod autoscaler, and it is currently using the built-in CPU and memory metrics. We have observed with our operations that these two metrics are not completely sufficient for Fluentd, and we are investigating to also use additional custom metrics to further enhance the horizontal pod autoscaler for Fluentd. There were certain cases where Fluentd did not react to the spike in load, and we faced issues. And this is the investigation that we are currently performing. There is another ingestion component that we saw, that's the data prepper. So currently we only have 2 of them. It's good enough for even for high ingest use cases. And depending on the plan size and the ingestion rate, we simply have to make the data prepper either larger or smaller. So, I mean, scale up and scale down. So this is sufficient in our existing use case, so we deal with 2 data prepper pods. And all these workloads are spread across 3 availability zones where possible. In most cases, we run on 3 availability zones. And for example, we introduce also restrictions and pod affinity policies and topology spread constraints to ensure that these workloads are always deployed in different availability zones. For the data nodes, we additionally also introduce zone-aware routing concepts. So in addition to physically deploying them on different zones, the application layer zone awareness is also enables that the primary and replica do not stay in the same zone. So this is the standard configuration. So this is the view of a single cloud logging instance. So we have on the control side control components. This includes the Kubernetes operator that takes care of provisioning and looking after the health of the instance, reconciling them when it's needed, and so on. And then we have the monitoring components that collects monitoring data, availability data, and then reports to the monitoring backend systems. Let's dive deeper into the roles of these components. The control components include several components, but for simplicity, I put them into a single module. They take care of instance lifecycle. So when I mentioned cloud logging services available in the marketplace, customer sees a UI where he can click, I need one cloud logging instance, and we have to provision, and this request reaches our broker. And once we receive this request, we need to take care of provisioning them into a Kubernetes cluster. So this is the provisioning task, and the next one is the binding task. The binding is a special request that asks or instructs the provisioned instance to return its credentials to the respective runtime that where the instance is created. So this is the place where we give back the credentials of, for example, the endpoints of Fluentd and its credentials, and the endpoints of dashboards and its credentials back to the runtime environment. And it also takes care of setting up the initial configuration of the cluster, like, for example, tuning them to high interest use case, setting up the identity provider configuration, and so on. Second, it also takes care of auto-scaling, like we mentioned, disk-based auto-scaling. When it detects the need for scale-out, it creates additional replicas in the stateful set. And then there are OpenSearch specific tasks, like, for example, we have a troubleshooting module that takes care of troubleshooting some of the known failure scenarios where OpenSearch cannot recover itself from. So running at this scale, it is not possible for us to manage individual instances for known hiccups. So we try to automate as much as possible into this troubleshooting module for known scenarios where OpenSearch would need a human intervention to make it out for. We can talk about it in the upcoming slides. So we have the troubleshooting and self-healing capabilities into the control components. We also take care of uploading the contents. The out-of-the-box dashboards and visualizations are then uploaded from these control components. There is also backup and restore of user contents, not the data part, but the dashboards, customer-created dashboards, customer-created configurations, map roles and role mappings, and so on. Then there is instance-specific activities that are also performed by these control components, like creating the needed certificates, rotating them when needed, and so on. We also take care of, the control component also takes care of assessing the health of the running instances and reporting them back to the control monitoring components. Let's take a look at it from a Kubernetes point of view. Let's go bottom up. Like we saw in the initial slides, we run on a variety of hyperscalers and sometimes even specially crafted data centers with special restrictions. We deploy on top of Kubernetes, and this is enabled by using Gartner. For those who are not aware, Gartner is a managed Kubernetes as a service. It's SAP's open source solution for managing Kubernetes clusters at scale. It is also governed by Neo-Nephos Foundation under Linux Foundation of Europe. CLS Cloud Logging Service uses Gartner to create and manage the fleet of Kubernetes service across different hyperscalers across the globe. So Gartner also offers other capabilities, like, for example, certificate management extensions and DNS management extensions and so on, which we leverage to create our Kubernetes cluster. Once the cluster is created, we have the control components installed into them. Like you see in the left side, there are these control components and monitoring components. Then we start deploying then we receive instance provision requests, and we start deploying OpenSearch clusters. Like you see, the dotted line represents a namespace. So we separate two instances by namespace. It is our responsibility to ensure that the namespace 1 cannot talk to namespace 2 by enforcing strict egress and ingress network policies. And on top, we also saw that there is 3 different availability zones, and it is essential when you are working in a high ingest scenario to define zone-aware routing also within other layers, not just within OpenSearch. For example, if Fluentd receives the request in a pod that sits in zone 1, it has to check if there is the destination residing where it has to send to is residing in the same node. If not, then it goes to the same zone. If not, it then goes to the other zone. So this ordering, priority ordering, is needed if you want to reduce the cost of inter-zonal traffic. So this we also have it enabled. This has the disadvantage that it might end up in an imbalanced way, but it saves a lot of cost if you're ingesting terabytes of data. And you want to avoid unnecessary round-robin based routing. That's the overview on how a Kubernetes cluster looks and how we deploy individual cloud logging instances across different namespaces. There is limit on how many nodes a single Kubernetes cluster can hold. And we also need to plan for the expansion. So let's talk about how it would look like when there is a need for more instances to be provisioned. So what we do is we have a detection mechanism or monitoring logic that gives us the input that, okay, it's time now you spin up a new Kubernetes cluster. Then we talk to Gartner API and create a new Kubernetes cluster, provision our control components into the new cluster, and wait for the new instance request to arrive. So this is the scale out of the Kubernetes cluster itself. But the problem you see here is that these are two different VPCs, two different setup, and they get two different domains and so on. So we would need a unifying concept that gives a single view for the end user. In the marketplace, there should not be differences visible to the customers when you are running on different Kubernetes cluster. This is enabled by our broker. Our broker is a region central component that's deployed once per region, and this takes care of receiving all the provision requests and then creating them into the respective Kubernetes clusters. It also takes care of scheduling them based on the available resources. It knows how many cloud logging instances are provisioned in a given cluster, what's the free space available, and it provisions it based on the resource utilization. There are also cases where older clusters deprovision some of the instances and have capacity left. It will then also try to fill them up. So this is enabled by this broker and scheduler. There are also limitations. So the broker scheduler is also implemented based on the Kubernetes operator pattern. So when there is an incoming provision request, a CR is provisioned, and the broker reacts to the CR, picks up the CR, and then it knows that it has to create a CLS instance CR into one of the Kubernetes clusters. As we grow with the number of Kubernetes clusters, sometimes we also notice that if there is a minor glitch in Kubernetes API access, then it affects the broker from scheduling the actual instance. This is okay if it's a new scheduling, but if there is a request for binding or credential rotation and so on, even 50 seconds of time taken would result in a failure of the operation. So this we need to take care of. Last year in OpenSearch Con, when I had presented some of the challenges that we are facing, at that time we were running 7,000 clusters, and we ran into issue of updating all 7,000 of them at once. We were doing that, and we also faced the usual shard issues that all of us face, and particularly when we have auto-scaling, we wanted to find a sweet spot where we give the number of shards according to the number of data nodes. So this is a problem that we also faced. And we had issues in curating the old indices. Sometimes so we have curation based on size. When let's say 80% of the overall disk utilization is achieved, we start deleting the old ones. So this had some problems that it did not always work, and few other problems. So I want to now talk about some of the problems, how we improved it in 3 layers, like the infrastructure layer, platform layer, and application layer. Let's start with the infrastructure layer. Like I mentioned, when we plan for a new infrastructure to host our workloads, we have to ensure that there are 3 availability zones for the default configurations to work. For us, when there are 3 availability zones available, it's also not sufficient. It's not fully sufficient. We need equal number of machines in 3 zones. So in some hyperscalers, you might find zone A and B to be fully capable of scaling out, and zone C, they have fewer machines. So this is not going to work, for example, in case where OpenSearch data nodes have to scale out. If the 6th node is up, it's waiting for zone C to be available. Otherwise, it waits there indefinitely. So we have to make sure that there are enough number of, if you are working on n number of zones, you have to make sure that there are equal number of machines in both. The other one is machine selection. So for example, our common size is M6i, 8x large or 16x large, but the sizing of the machine selection is, for us, is determined by the number of mount points that it can allow to its persistent volumes. So even if you have extra memory and CPU to spare, you cannot provision an additional OpenSearch data node to it because it cannot mount to a disk. So we took this number of mount point as the base, and from there decided what CPU and memory would work out for us, and chose the machine that fit that size. And the next one is scale out of nodes within the Kubernetes, within a single Kubernetes cluster. Let's say we have packed a Kubernetes cluster with 10 machines. The Kubernetes cluster can scale up to 100 machines within itself, but the trigger to scale out to a new virtual machine happens only when there is an inability to provision a pod that is coming in. So this might already be too late when, for example, there is a high ingest use case and you want to actively scale out your data node. So you have to plan. To overcome this. You can either do so by over provisioning, or you can proactively scale out your Kubernetes node when there is, let's say, 50% utilization, or even better, you can have placeholder pods. The pod that takes up the size of a node, but it has a low priority. Whenever there is a need for machine for a high priority use case like OpenSearch data node, the spot gets kicked out, and immediately you acquire a machine with for your OpenSearch data node. So these 2 approaches are helpful to further reduce the time it takes to detect the need for scale out, actually scale out, and then provision Kubernetes and the workload on top. The other one, now I spoke about adding more nodes within a single Kubernetes cluster. Other one is also you have to take care of when to add a new Kubernetes cluster. Like I mentioned, you have to find an optimal size which allows existing instances to also scale. You cannot fill it up to 95% and then go to a new cluster. You have to take into account what would happen if all the 200, 300 OpenSearch clusters within a Kubernetes node decide to scale out to its fullest. And you have to find the right sizing and get alerted or notified when it's the time to go to a new cluster. If you go to the platform level, like you saw in the picture, the control components are centrally deployed per Kubernetes cluster. So we have over 300 plus instances or OpenSearch clusters in a single Kubernetes cluster, and there is just one operator, Kubernetes operator, taking care of reconciling them. And there was, in the past, a single instance that is taking care of it. Because of the combination of tasks that it is doing, it sometimes got stuck in an endless reconciliation loop. Meaning, there are back-to-back queuing of low-prior tasks, which ate up all the workers and resources that the OpenSearch operator could do. And when there was a critical task for it to perform, like auto-scaling or provisioning a new instance, it was not available to act on this. And the OpenSearch operator the operator that we use held two different responsibilities. It was taking care of the Kubernetes-related tasks, and it was also taking care of OpenSearch-related tasks. So this is a mix of responsibilities. What we also saw is that it could not handle a burst of updates. Let's say there was a version update or a change in the plan size. It blindly applied to all thousands of instances at once, and the Kubernetes responded by restarting it or performing rolling updates. Even with a pod disruption budget and all policies in place to prevent outage within a single cluster, if it removed one data node from each of the thousands of instances, we would need, for example, more virtual machines to move them to and then perform the update and reschedule them back. And as I mentioned, we control over 60,000 persistent volumes. The hyperscalers also throttle the API request to remove and deattach disks and so on. So sometimes we will be throttled and the update waits forever and it takes a longer duration. So in summary, there was no progressive rollout concept in our operator. Also, there was no throttling and no order of updates. So in several cases, it is very important that you update OpenSearch clusters in order. So first you want to tackle data nodes or master node or cluster manager, and then update others. But this ordering was not possible. If we mentioned it has to go to version 2.19, it simply updated all of them. So this knowledge was not given to Kubernetes. First, we try to address the separation of concerns. Like I mentioned, the operator had two responsibilities. The Kubernetes lifecycle management, like provisioning the instance, taking care of replica count when there is auto-scaling need, deploying the parsers, and so on. It also did OpenSearch domain-specific activities like content reconciliation, backup of the contents, troubleshooting, and so on. This created a problem that, for example, the left side is always you describe the state and then you forget about it. It's not going to, even if it's failing, it will not stall, it will not block the operation. But on the other side, with OpenSearch, let's say if it's trying to create a credential into OpenSearch database, and one cluster, for some reason, is red and it cannot create a password. So it causes a failure in this action, so it might have to either retry or put it back into the queue. So there is a mix of two different responsibilities. So the first thing that we did is to move the domain-specific responsibilities to a different component called maintainers. So the maintainer is then responsible for performing OpenSearch or the instance-specific activities, like taking care of all the activities that were previously done by, shouldn't have been done by operator, into the maintainer. And maintainer is the one that talks to the instances and keeps it in the proper state, and it will not perform any activities that needs to be done at the Kubernetes level. And if you look at the picture on the right, the maintainer is deployed per namespace. So it has a responsibility to take care of a single namespace and single instance, while the operator still stays in a play and stays in the central cluster. After this change, we saw huge improvements in performance. For example, the maintainer is quick in fixing troubleshooting issues. Maintainer can upload dashboards, reconcile them faster, and so on. If I have to quickly go through the responsibilities, like the operator, we made further improvements there by making the status implementation more accurate. In the past, we had a 0 or 1 status implementation. Either the pod is up or pod is down. The status more reflected what the Kubernetes view of the pod is and not the OpenSearch view on it. This leads to also both false alerts and also issues in throttling. With respect to false alerts, for example, even if there is one pod down, we have replicas in a different zone, but it should not be reported as a down. So it had to be zone aware and know that we could survive the failure of one node in a different zone because we have replicas elsewhere. And the other one is when we provision an instance, for example, it's starting slow. There are data nodes added one after the other. So this should not be taken as a failure scenario and reply and respond and create an alert that instance is down. It will take a few minutes until the new instance is provisioned. So what we try to do is inject into the status implementation also the proper lifecycle knowledge. So instance being created, instances in progress, instances migrating, and so on. This effective status implementation allowed us to perform throttling. So, for example, when we want to update all 1,000 instances, we simply say, okay, first update 50 instances. And when we know the number of instances that are in progress state have switched to succeed state, we then move to the next 50, or we slowly increase the throttling. And by doing so, we are able to control the problems that we had in the past by avoiding burst of API requests to hyperscalers, detaching too many pods, and so on. And with the latest implementation of Operator, we also leveraged the capabilities that came with the latest controller runtime, like monitoring of the workers and also leader election. And we run the operators in 3 replicas. The maintainer does the task of content management. It uploads contents, and if users are overriding the default contents, it is also able to reconcile them back to the default contents. Like I mentioned, it does troubleshooting. Like, for example, if it tried to do a shard reroute and gave up after some time, we take care of triggering the reroute again. If there is a wrong or incorrect implementation of replicas overridden by the customers, we then take care of ensuring that the right amount of replicas are available. It also fixes 2 challenges of size-based rollover. So when there is a high ingest scenario where a customer ingests too much within a single day and fills more than 75% of its current overall capacity, there is a problem that we delete the complete index that is on the complete write index on the current day. So what we did is we enforced a shard size-based rollover. So when there is a limit, we specify a limit, and when the limit is reached, we roll over to a new index. And many such capabilities are then part of the maintainer component. I want to highlight some of the other points that we noticed is that whenever there is an update to the SAML configuration, all 10 OpenSearch pod made connections to the IDP and try to download the SAML metadata. So it is okay if you do it in a small scale, but if you have thousands of the instances talking to the metadata server and trying to fetch them for every single update, then it becomes problematic. So what we did is implement an egress controller that takes care of caching the requests. So OpenSearch pods talk to this controller, and it only gives back a cache response. There is also drawbacks that it has to wait for 5 minutes for the update, but this is solving the number of requests that go to the IDP. The other one is alerting webhook that goes out. We have to be careful that the OpenSearch webhook post request can also talk to internal endpoints. So we have to be, even though it's a GET, there are possibilities to also work around them. So we have to be careful to also design our network policy that the webhook is not talking to other components within your cluster which are not protected by authentication. Last one is the rejected index improvement. We noticed that one of the biggest pain point is to handle mapping conflicts. When there is ingestion and it's not accepted, it falls back to the ingestion component, and it's putting burden on the ingester. Instead of rejecting just one document, it rejects the complete batch. It eats up a lot of resource and blocks other vital data coming in. So what we do is, if we cannot ingest it, we quickly put the raw data into a rejected index and continue with our ingestion. So these are some of the steps that we took to improve, and we are working on some new topics like storage tiering, scaling the hot storage to also support petabyte scale, and several new topics. I would highly recommend the talk Enhancing Application Observability with OpenTelemetry from OpenSearchCon Europe this year. It's a very interesting talk if you are starting your journey with OpenTelemetry and how to do it and so on, by one of our team members, Carsten Schnitter. If you have, I know I'm running out of time, I want to drop the names also of the OpenSearch for the operator implementation, and also for shards and index rollover handling. We have specific experts. You can reach all of us through OpenSearch Slack channel if you have more questions or you want to collaborate, for example, at conceptual level when designing Kubernetes operator. Thank you so much for listening.